Welcome to the second part of Lecture 1. And we're going to start looking at our subatomic particles, more specifically, our electrons, and look at how they move and how we define their movements through mathematics. So one of the things that people started to notice, specifically people, Louis de Broglie, noticed that electrons possess wave behavior. And he did this with something called the double slit experiment. Now, also, they knew already that electrons possessed a mass. And so now we had something with mass that possessed wave behavior. This made it very different than what they noticed with light, which, as far as they knew, had no mass, but also exhibited wave behavior. And the way that de Broglie saw that the wave behavior of electrons is he passed a beam of electrons through a pair of narrow slits, and instead of just seeing two hits of a electron beam, instead he saw interference patterns, just like he would see with a single beam of light passing through this double slit. And so what they actually see is that electrons interfere with themselves, which is a very kind of strange concept. If you take some more physics classes that explores quantum mechanics a little bit deeper than we do, you will certainly look at some of the implications of that. But when we started looking at the idea of mass having waves, traveling as a wave, it began to lead to some interesting principles. Specifically, this idea of a de Broglie wavelength, which means that any particle that has a mass and has a velocity will have a wavelength. So anytime something is moving, it will have a wavelength. This includes you walking down the street. You have a wavelength as you move walking down the street. It also leads to the idea of the uncertainty principle. We'll explore that in a little bit more detail. And then the other thing it leads to is something called indeterminacy, which we will also talk about. Let's look at this idea of indeterminacy. So things can be deterministic versus non-deterministic. Basically, it means, do we know something for sure or do we not? And you can put it in terms of quantum mechanics, in terms of classical mechanics and quantum mechanics. Classical mechanics would be the type of physics that you studied most likely in high school, where if you have a cannon and you shoot the cannonball out at a certain angle with a very certain velocity, you can calculate where exactly it's going to land. You can't really do that with quantum mechanics because you have this idea of indeterminacy. When you have a cannonball, that cannonball will follow a trajectory, and we can calculate that trajectory. It's one of the reasons that we can put men on the moon. We can figure out where comets are going to be. We can shoot satellites out to take pictures of planets a long ways away because we have their trajectory measured, and we know exactly where something's going to be at a very specific point in time. With quantum mechanics, the best that we can do is a probability of where something's going to be at a certain period in time. So our electrons and atoms have very well defined energies, so we can measure their energies out to quite a few decimal places, but we cannot calculate their positions or their trajectories. By trajectories, we mean their paths. So the reason for this is because a given energy has several different positions with the exact same energy. And so with all those different positions, there's no way to know if an electron will be in one particular position or some other particular position. So here we see our classical trajectory here. So this might be like our cannonball being shot from a cannon, following an arc. We could actually calculate its position at any given time. We could calculate the vertical and horizontal velocity at any one of those given times using classical physics. However, a quantum mechanical distribution map would look something like this. Now we see that we have a general probability along the exact same arc, and there the probabilities are densest. So that's probably going to be where our cannonball would follow. However, there is also a chance that it'll be down here or over here or up here somewhere during the course of its travels from one point to another. And so the best that we can do when we're looking at electrons is to map out its probability of where we are likely to find the electron based on its energy. If we look at a more common way of looking at indeterminacy would be watching American baseball here. Where does the baseball land? Now, if the pitcher is trying to hit it right there, right into the catcher's mitt, most of the time it goes there, but sometimes weird things happen. Maybe it catches on his fingernail and ends up out here. Maybe a gust of wind happens and it blows it out here. Maybe his foot slipped a little bit and it ends up out here. Those things don't happen very often, but they do happen occasionally, and that pitch does not always go exactly where we think it's going to go. So the best that we could do, knowing where the pitcher is and what kind of energy that ball is going to have, we would have to make a probability map of where we think the ball will end up when it reaches the catcher. Most of the time, it'll be in the mitt, but not every time. And so in a way, the pitcher throwing the baseball follows a quantum mechanical strike zone. Now, in order to describe these motions of electrons relating to the total energy of the electron, in terms of math, we have something that is called the Schrodinger equation. And the Schrodinger equation looks at the total energy of the electron, the actual energy of the electron, and the wave function of an electron. And the wave function is nothing more than a combination of exponentials and sine waves used to describe the motion of an electron as it goes around an atom. It is a three-dimensional wave function, so it is fairly complex, and it does have components in the x, y, and z direction, or sometimes it's put into radial coordinates as well. So here's the Schrodinger equation. It looks fairly simple, where we just have H psi is equal to E psi. However, it can be expanded. We're not going to expand it here. You might see that in a later course. But that H is the Hamiltonian operator, which involves all of the differentials, the second differentials that I'd mentioned, where you're taking differentials of all the different parts and pieces of that equation. The wave function itself is that combination of exponentials and sine waves. The E is the actual energy of that electron. And so if you can get H psi to equal E psi, then the psi, you now have a wave function that will describe the motion of that electron. Now, it looks like a fairly easy equation to solve. However, we can only solve it for one single electron going around an atom. As soon as an atom has more than one electron, the math becomes too complex because we have no way of accounting for the electron pair repulsion that those electrons will encounter as they come close to each other, since they both have negative charges. So we have no math to describe that interaction. Maybe someday we will. Maybe one of you will solve that equation later on in your life. But for right now, we can only solve it for a single equation going around an atom. So if we take that wave function psi, we can make approximations, by the way, where we can solve these equations. We do have some colleagues here at MSP that's where their research lies, is working with those types of programs. And one of the things that they do in those approximations and the calculations is they plot the wave function squared. And when you plot that wave function squared, so that's psi squared, you get what's called a probability density map of where the electrons should be. And we call this an orbital. And you'll hear me use that term quite a bit as we start moving more into quantum mechanics. So as I mentioned, we can only solve that Schrodinger equation for an atom with a single electron. And so that would mean that we'd have to take several electrons away from any atom larger than hydrogen. A naturally occurring hydrogen atom has only one single electron, so we can solve the Schrodinger equation exactly for a hydrogen atom. And what we end up seeing is all of these psi functions and psi squareds, and we get these orbitals. Now, we mentioned that the orbital is a probability density map of where to find an electron, but what it also then represents is a graphical representation of that wave function that solves the equation, and that gives us something to visualize, which becomes very nice. Now, when we're solving that equation, what we find is each of those orbitals has three related quantum numbers that define the wave function. We have the principal quantum number, which we designate n. We have the angular momentum quantum number, which we designate L. And we have the magnetic quantum number, m sub L. So those three variables plugged into a particular equation will solve the Schrodinger equation for a hydrogen atom. Now, it turns out that we do have a fourth quantum number in there. It's not part of the Schrodinger equation, but anytime we are describing the quantum numbers for a particular electron, we do need to include this fourth value, which is called the spin quantum number, and it has a designation of m sub s. Let's look at each of these quantum numbers in a little bit of detail. So that principal quantum number, n, is one of the most important quantum numbers because it determines both the size of the orbital and the energy of the orbital. It has certain allowable values, but it has a fairly wide range. It can be any integer greater than 0. So n can have a value of 1, 2, 3, 4, 5, 6, 7, etc., all the way up to infinity. As the value of n goes up, the energy of an electron in those orbitals goes up, and we can calculate the energy of an electron in one of those orbitals using something called the Rydberg equation. So the Rydberg equation says that the energy of an electron in an n orbital, so n is equal to 1, 2, 3, 4, whatever, is equal to the Rydberg constant, negative 2.18 times 10 to the minus 18 joules, times 1 over n squared. And the n squared that's here comes from the n value of whichever quantum number shell you happen to be in. So here, if we see the calculations for an n equal to 1, down here, for n equal to 2, energy goes up quite a bit and becomes a little less stable. N equals 3, n equals 4. And you notice a couple of things here. See that the energies of the subsequent orbitals are getting closer and closer. That does not mean that the orbitals are getting physically closer and closer, just that the energies are. But that means it makes it easier for an electron to jump between orbitals as we get higher and higher up. We can look at the second quantum number here, angular momentum, which is an L. It determines the shape of the orbital. It also has a certain allowable set of values. The values for L start at 0, so you can have an L equal to 0, and they can go up as high as n minus 1. So for a given principal quantum number n, your allowed value for L start at 0 and go up to the value of 1 less than whatever your n value is. So L can have the value of 0, 1, 2, 3, etc., up to n minus 1. So if we have an L that is equal to, or an n equal to 1, so your very first principal quantum number, then L has to be 0. That is the only possible quantum number for L if n is equal to 1. If we go to an n equal to 2, well, then we have two different possible values for L. It can equal 0 or it can equal 1. Okay, one of the more common errors I see is that people think that it has to be equal to n minus 1, but that's not true. It starts at 0 and can go up to n minus 1. And one way of looking at that is whatever the n value is, that's how many possible L values you have. So if n is equal to 1, you have one possible L value. If n is equal to 2, you have two possible n values, or L values rather. Okay, so again, the number of possible L values always equal to n. Now, instead of memorizing what the L value is, or looking at what that value is, and trying to remember what the shape is, a lot of times what we do is we relate that value of L to a letter designation that actually has its roots in some spectroscopic observations way back in the early 1900s. So very frequently, if an orbital has a value, an L value equal to 0, we call that an s orbital. It has a very specific shape. If L is equal to 1, we call that a p orbital. If L is 2, it's a d orbital. And if L is 3, it's an f orbital. It actually keeps going up from there, but that's really all we need for this class. So we've done N, we've done L, and now we start looking at the fine tuning of things, and this is the magnetic quantum number, m sub L. This is the third quantum number that we use to solve the Schrodinger equation. And m sub L determines the orientation of a particular orbital in space. So if you can have more than one orbital present of the same type, then they must differ by their orientation. Okay, m sub L has integer values that range anywhere from minus L to plus L. So let's say that we have a p orbital, and a p orbital has an L value of 1 based on that previous slide. So m sub L can go from minus L up to plus L, and it can pass through 0. So it's going to have values of minus 1, 0, and plus 1. This means that for a p orbital, we can have 3 different p orbitals, all with a different orientation in space. It turns out they point in 3 different directions along the x-axis, the y-axis, and the z-axis. If we have L equal 2, so we go to a d orbital, we see that m sub L can go from minus L to plus L, so from minus 2 up to plus 2. So we have minus 2, minus 1, 0, plus 1, and plus 2. Those are all possible values. Our last quantum number is the spin quantum number, m sub s. So this specifies the magnetic spin of an electron when it's in an orbital. It has 2 possible values only, plus 1/2 and minus 1/2. And we refer to that as spin up and spin down. So this number is much more important when we start occupying the orbitals with electrons, and we don't even use the plus 1/2 and minus 1/2 in this class. That's just what they are. But we do think about the idea of being spin up and spin down. Now, when we're referring to individual orbitals where we're putting electrons into them, which is what we're going to focus on primarily in this class, we generally look at those orbitals strictly by N and L. We don't worry about m sub L quite so much. And so the L value is generally reported as the letter designation instead of the number designation. The number of sublevels that we have are going to be equal to the value of n. So if we have an n value of 2, then we're going to have 2 L values there, and we're going to have 2 values for L. So we would have an s orbital and a p orbital for L values of 0 and L values of 1 if we are in n equals 2. The total number of orbitals within a level would be equal to n squared. And the number of orbitals in each sublevel is going to be equal to 2 times L plus 1. So that finishes out our discussion on the second part of Lecture 1. A little bit in that last slide might be a little out there for you. I certainly recommend that you take a look at your book for some examples, maybe a little bit more specific pictures that you might be able to find. If you have any questions on that, make sure you contact either me or your tutor.